This is Office Hours,
a show for sharing experiences and stories in governance, risk management, and compliance. All right, Kevin. Hope everybody else brought their beer today. This one's gonna go a little more in depth than our last couple have.
Are we gonna get nerdy today, Dan?
Maybe a little bit. So, the fundamental thing I want to talk about today is I don't think particularly, especially for outside of financial services, bankers and insurers, we really don't, as risk managers, auditors, other types of risk professionals, I see way too little usage of scenario analysis. My argument would be if we can't do basic scenario modeling and use that to analyze or predict the possibility of potential outcomes, that I think we're not really prepared to do real risk management.
Sure. So going back to the insurance example, it'd be like trying to develop an insurance policy without analyzing the potential of a hurricane and what you'll have to pay out.
Totally. How much are we really managing the risk? So in this case, what we're going to do today is do some basic scenario modeling with ACL Analytics around what was just came out in the press, a case from the state of Arizona with their lottery system. So today we're going to talk about scenario modeling and whether or not the lottery is actually fair or is actually random. With that, risk scenario modeling and winning the lottery. I'm Dan, and this is Kevin.
Hello.
Welcome to Office Hours. This link goes to the case study that we're going to talk about today. It's totally public, just released on the State of Arizona Lottery's website. And we're going to use some basic data analytics to investigate the concerns that were found here. If you just Google Arizona Lottery RNG report, you'll find this report, and it's really helpful background on what I'm going to accomplish here. But I'm going to try and explain it without reading the report. It's only a 2 or 3 page executive summary audit report. So why are we doing this? This one's going to go a bit more in depth, so I want to give a little bit of an executive summary about where we're going to go here. This is a really good example of a case for risk analytics and a real but publicly disclosed risk incident, and one I think we can all relate to, the randomness of the lottery. I'm not a lottery player myself, but surely it should be random.
Yeah, I would hope when I buy a lottery ticket that I can have good faith that those numbers are random.
So we're going to take a look at this case study, look at what they called out as the key risks, and then going to do some work to just explain quickly statistically define what does random really mean and how that affects the lottery. Now, how is the lottery really the most important use case for this? No, not at all. It was a public example. But the notion of randomness as a concept is really applicable to, as most financial statement auditors know, it's really important in how we use randomness to select samples and getting confidence in an audit result. But areas like data encryption, it becomes really, really important. So hopefully you pick up along the way a couple of useful points about just the general importance of and what actually is randomness. And then finally, how. So what we're going to do is actually do a scenario analysis to compare the outcomes of an actual scenario, to compare the actual real world outcomes of the lottery draws, compare it to the scenario analysis and see how likely was it that we had a problem. So I'll be rebuilding and testing what was described in that audit report with ACL Analytics to validate how likely that actual scenario should have been. And then I'll try and point out along the way a number of ACL tricks for the more advanced among us. We'll definitely be using some scripts today, scenario simulation, looping, the execute command, doing some import of data directly from the web. I definitely leverage some ScriptHub scripts through this for those who know what ScriptHub is, connecting to Tableau, etc.
So we're going to learn about randomness, about scenario analysis, really pointed at lottery. But Dan, are people also going to be able to take some of the techniques today and point them at different use cases?
Totally. Great point. This we can all understand the lottery draw, but you got to think about applying scenario analysis to anywhere where you find it difficult to quantify risk, or where you want to be more predictive or forecastive, as I like to say, about risk. Same principle applies, and the 3-step process I lay out later on should be applying to each of, I would argue, at least key. Maybe not time to do it on every operational risk, but at least key top-level strategic risks, which surely picking the numbers for the lottery system actually is. So with all that, I've already made the disclaimer, but we don't have any internal knowledge. We have no involvement with the Arizona lottery situation, and really haven't read anything about it beyond what was just in this public audit report. Just simply made a good case study. So take that for what it's worth. I'm sure there's much more to the story than what we are involved here. So to get going, there was 2 incidents laid out in that audit report that we're going to talk about today. The first one was that the first incident was that back in October, the Arizona State Lottery officials notified the Multi-State Lottery Corporation, I think that's how you refer to it, that the same game numbers were repeating on consecutive draws. So 4 of the different Arizona lottery games were affected, and basically 4 times in a row or multiple times in a row kicked out the exact same draw numbers. So Arizona and the Multi-State Lottery Corp, they investigated, isolated the issue to one particular machine, removed and secured it. So for testing. So what actually happened there? Well, that's where the notion of what is randomness comes in. So Kevin, I have a trivia question for you.
Uh-oh.
Don't be guided by Dilbert here. Can computers pick random numbers?
Yes, computers can pick random numbers, but with a caveat that they're not truly random, because you need to input something into the computer.
I didn't actually prepare him for that answer, and you almost missed it and saved yourself at the end. Computers can generate almost random numbers, not actual random numbers. And so that gets to a question of, in cases where randomness is necessary, how random is random enough? If that makes sense.
Yeah.
So in the case of the lottery, computers probably can generate plenty random enough numbers to be valid for purposes of the lottery. But for purposes of data encryption, where a malicious actor might take a block of encrypted data and run millions, billions, trillions of iterations over that data to try and find patterns in the randomness of the encryption that would allow them to find a path through the encryption algorithm, it really, really matters. Now, so what does that mean? Obviously, computers are what do encryption, so that seems encryption is dependent on randomness, and so therefore it seems problematic. It seems problematic that encryption would ever be good, and this is ultimately how vulnerabilities and things like that emerge in data encryption.
Yeah. So how do they get around that in terms of encryption, or how do they make it better or more secure?
There's 2 ways, and this diagram lays out. The first part is encryption algorithms are basically this bunch of stuff in the middle, which is there's a bunch of fancy names there. I'm not going to go through it. There's basically a bunch of crazy math. So this is the reason some encryption algorithms have been cracked, is because the math is not good enough. The math is not, for lack of a better term, complex enough to generate adequately to remove patterns in the resulting data on a large enough scale.
Which is why they keep coming out with stronger encryption algorithms.
Right. That's
as
exactly
computing
right.
power gets stronger.
Exactly. The other part, though, that's equally important is this notion of a seed. So all random number any real random number generator, random number generation program on a computer, that crazy math, is run off of a piece of seed data. So ideally, the seed data, like the math, you want to be as unpredictable as possible. So typically, encryption algorithms on a computer will take measurements from your computer to generate that seed. Things like what's the exact time and date stamp, or what's the temperature of the processor in the computer. Things that are in my machine that could be difficult to predict adds entropy into the seed, and along with the entropy in the math makes it very, very difficult to crack. So that means seeds ideally need to be unique and unpredictable. And you probably see where I'm going with this. What happened in the case of, in this audit report, what they found at the lottery system was they'd actually gone a step further. And they said, we're not happy, no matter how good computers can generate random numbers, we're not going to do a purely computer-generated random number. We want true random numbers. So they were going to use the seeds, run the random number generator math off of those truly random seeds. And the way they'd pick those truly random seeds is in topics like quantum mechanics. There's phenomena that occur in quantum mechanics. I'm not going to pretend like I understand this shit. But in radioactive decay, it's truly random what the molecules are doing as they decay. Some scientist is totally going to correct me on that. But the point being that if you look like this and you have a Geiger counter, in this case a model RM60 Geiger counter, you can detect activity in radioactive decay, quantum mechanic activity that is truly random, and use that to pick real seeds.
Interesting.
Does that make sense?
Yeah. Did they actually go through all of this to pick the random seeds for the lottery?
So that's exactly right. So those machines apparently had another, it doesn't actually look like this, I made this up.
Okay.
Actually have a piece of hardware attached to them that would make radioactive measurements. God, I must sound so stupid to a real physics major. That would make radioactive measurements of a decaying element to find the actual true randomness. And then that would get kicked into the super complicated math to generate the lottery draws.
Right.
So what that paragraph said is when they went out and looked into this, so that much complexity, how is it possible? They took every step in my non-scientific, but as a risk professional opinion, to generate random numbers.
Sure, but you explained it well enough to me that my conclusion, although I don't know what it is, and I'm hoping you tell me, is that the single point of failure is the machine. So if the machine gives back the same reading multiple times, even though that might not be the actual reading, the machine's faulty, it might give you the same reading. Think of a clock when the power goes out and it just flashes the same number over and over again.
That's very close to what happened. So, and believe me, I actually did not prime Kevin at all for this because I wanted to make sure we drew this out a bit for clarity. The machine, that thing, the RM60, whatever that is, Geiger counter thing, didn't work. And so the software that fed the random number generator, fed the complex math, fed in 0 every time.
Oh, okay.
So every seed was 0. And so no matter how complex the math is, when you run 0, when you start it off of 0, it turns out to be 0 every time because you started from absolutely no entropy. So I put a link down here if you're really a nerd and you want to get into how quantum mechanics and this measuring radioactive decay and all that sort of stuff could actually theoretically create unbreakable encryption. There's a really good Wired article there on it. But in this case, the real failure wasn't that the machine failed. It's that why didn't we either then stop the drawings, or why did we not feed in some other seed that would have likely been plenty random enough for purposes of the lottery, the temperature of my CPU, whatever the case may be.
Yeah, and you got to think that they should have had some control in place to alert someone if the seed was 0. which
Right.
doesn't seem like a
Right, and not in the place to say that I'm some expert on the lottery and their internal control processes and what would be appropriate, but this turned out to be detective. We didn't pick up the risk event until several straight draws had generated the same.
something happened that they didn't expect to happen, and somebody eventually looked at the seeds and found the root cause.
Yes. So that's a typical sort of audit issue. That could happen in any of audit issue, risk event issue. Something along that line, I feel like could happen in any of our organizations. No matter how good our IT general controls are, sometimes computers do things that we hadn't anticipated and cause a failure like that. That's not actually what I want to look at. What I want to look at is the second incident in their report. Now, take this incident as background. Consider that this had just happened, or translate it to the kind of event that might happen in your organization. So, for example, if we had an incident where a email went out one day to the entire company that said we had to physically remove an intruder from our secured on-site premise, we'd probably all walk around the building for the next few days hypersensitive to people we don't recognize in the building. Does that make sense?
Yep.
So that's what happened here. Is with that newfound vigilance that resulted from the prior risk event, all of a sudden in a separate game, the Arizona pick 3 numbers generated the same number set, not in a row like in the previous case, but 3 times or a number of times, I guess 5 times total, in a relatively, what was considered a relatively short window. However, it was a different machine generating these lottery picks. Same make and model, different physical machine.
Interesting. So what was the problem on the second?
So according to the audit report, they said according to the audit report, there was no problem. They said we actually looked into the second scenario, pre and post draw, brought in an outside statistical expert to evaluate how likely that would have been to happen, and they said they would have found these results to be within potential norms. And so out of caution, we removed that machine anyway, but we elected to think there's probably not a problem here. So that seems substantially odd to me. So that's where it piqued my interest. I read this and I said, it drew 804 5 different times in a relatively short window. I don't buy it. Is frankly what my auditor sense, my auditor spidey sense tells me.
Right. So you think maybe the statistician or someone might have missed something, or potentially there's a way we can test this?
Exactly. Or I'm interested in it for academic reasons of, is this possible? And it seems like a great case for scenario analysis. And back to the original point, which is we should all be doing more scenario analysis, especially in a time like this where a potential risk event has come up, or even better yet, hasn't yet emerged, but we've recognized could be a future risk event that we're highly sensitive to for strategic reasons, as was the Arizona State Lottery in this case. So this language is straight out of the audit report, and I'm going to read it quickly. The investigation objective and scope was an independent statistical expert was engaged to evaluate the probability and frequency that 3 numbers, each ranging from 0 to 9, would repeat within a draw population of 742 events. The purpose of this exercise was to determine whether actual pick 3 results were consistent with predicted outcomes. So that means there had been 742 draws. Each time they draw, they pick 3 numbers, 3 integer numbers, 0 to 9, for that draw. So their results are, for example, 168 is a potential outcome. So the investigation and conclusion, again, straight from the wording in the report. Furthermore, and this is the key, if we go back to our full set of 742 observations, this was the conclusion. It is not unreasonable to have a small set of 3-digit numbers occur 3, 4, or even 5 times among the set of winners. In our data, no set of numbers occurred more than 5 times, with only 2 numbers occurring exactly 5 times, 804 and 919. Thus, it's within the realm of what might occur naturally for 804 to have occurred 5 times between 715 and 1117. Does that make sense?
Yeah, I'm just trying to think about I'm trying to do the probability math in my head. I don't know if you have already looked this up, but I know for 649, it's like 1 in 13 million is the chance to draw your 6 numbers out of 49.
And there's enough math in here that the math actually gets complicated to say, to come up with the exact probabilities. Now, even though that's the case, the math gets complicated. The other thing I don't like about just purely doing the probability math is that approach works here where we have a pure probability problem.
Right.
In other cases where there's not pure probability, we can't just do that. We have to inject changes in variables.
Right.
Right? And so that's why scenario modeling is so impactful, is it's not based on pure math. More importantly, it's not based on gut instinct.
Yeah.
And perhaps most importantly of all, is it gives you a set of outcomes at the end that you can compare your events to very naturally think through how does my event fit in the broader picture. Does that make sense?
Yeah. And then another thing you can do with that scenario analysis, if you have particular inputs that are applicable to you, like if you're looking at financial modeling and seeing how, say, price change might change different outcomes, you can just change the input parameters, get a different spectrum of outputs, and then use those to make better decisions or assess risk.
How does interest rates affect our fixed income portfolio if we're a bank? How would a change in pricing affect our customer retention if we're a subscription-based software company?
Yeah.
This is where scenario modeling changes the game, and so many auditors and risk managers need to do so much more of this. So, moving along, we've already talked too long. So the interbasic scenario modeling. To rephrase the problem, out of a population of 742, Arizona picked 3 lottery drawings. The winning combinations of 804 and 919 each came up 5 times. That's the total information I have in this case. That was what was in the audit report. Intuitively, though, my spidey sense goes off. Only 742 draws, and 10 of them were these 2 number combinations. I immediately jump to machine's broken, or there's a fraud being committed, an Office Space style fraud, right?
Right.
Where we put a bug in the computer, and Kevin's a child of the 90s. He knows Office Space. So fundamentally, only 3 steps to doing this, right? Step 1. We model the scenario. The 742 random drawings of 3 numbers, each number from 0 to 9. Second, run that scenario. This is the key, and this is why you have to have a bit of technology here to do this, is run that same, now that you've created that model, run that model or run that scenario 1,000 times. This is what I did, run it 1,000 times. Even better if you run it 10,000 times or 1,000,000 times or a gazillion times. The more you run it, the more probabilistically accurate your scenario is. That's a word I made up, just like forecastive. That lets us see what a distribution of potential outcomes looks like of these draw results. And then 3, now we compare that to, in this case, our real-world risk event to see how fishy is that risk event. Or, more importantly, if it was a future event, look at that distribution and say, how much of that distribution can we not stomach, and what are the odds of it happening?
Right. So basically, we're going to run a simulation of these 742 lottery draws, I don't know, are you going to do 1,000 or 10,000?
I'm going to do 1,000.
Okay, we're going to run that 1,000 times, see how many times the same number combination comes up, and compare how likely we think this is to be a real-world scenario.
That's right. Okay, so first off the bat, we're going to get good seeds.
How are we going to do that?
So given what they were doing, I wanted to get true random seeds, or at least as close to true random seeds as I could get. Also, I frankly wanted to make my life easier and save myself some data analysis, some math writing to generate the random numbers myself.
Right.
So great news. There's this fantastic site called random.org. It's a random number generator. It certainly would claim to be, and for all intents and purposes by me, it is true random numbers. They don't use radioactive decay in the same way, but they use basically measurements of atmospheric noise, which is a sciencey thing that is truly random, to generate truly random numbers. And so right off the bat, I'm just going to run over here to the random number generator. So this one is for random integers, but it uses all truly random seeds. And so we had 742 draws times 3 numbers, right, in each draw. Mm-hmm. So there's 2,226 random integers is what I'm looking for. Each one has a value between 0 and 9. And I'm going to format that into 3 columns, one for each, so that there's 1 row for each draw, and get the numbers. So there we go. Right off the bat, I've just cut out 90% of the work I've just cut out a ton of work because random.org does this awesome job. And that really goes to step 1 I had back there on the PowerPoint, which was create a model. Create a model for generating the real world events. So that's what I did. This is one of the 1,000. One population of 742 draws that could have been a potential outcome of those 742 draws. So I'm just going to copy those. I'm going to go over to Ace. Actually, I'm going to just run over here real quickly. I'm going to throw in here a new text file. Manual draw simulation. Throw that here. Save. Okay. Now we have a text file with our first simulation. Come in here, import it into ACL. So I just need to find that file. It's in my source data. Open that. Detects that it's a delimited file. Detects that it's a tab file. That'll work just fine. I'm going to call this. I'm going to put this in my source data, and I'm going to call it the manual simulation. First, that file didn't have column names in it, so I'm just going to give it slightly more meaningful column names. Third, next, finish, done. So there's my first draw in ACL.
There you go, Dan's Lottery Corporation.
Dan's Lottery Corporation. So, yeah, effectively replicated what we've done our best here to replicate what those machines do. So now from here, the first thing I'm going to do is I'm just going to add a field here, and all I'm going to do is I'm going to call this field the draw results. And basically what I'm going to do is I'm just going to collapse those 3 numbers together in a string so that I can sort by the draw results in the same order they're in, right? So I'll very quickly convert what is a number now to a string. I'm going to concatenate that together. And now, first thing I'm going to do is now look at those draw results, right? I'm going to classify those. So right off the bat, now if I go and quick sort these, right off the bat I see, okay, in my draw there were no cases in this 742 draws, there was not any cases where 5 times the draw matched, let alone 2, like in our example or in our real world scenario. On board so far?
Yeah, but you do have cases where 4 happened.
Several cases where 4 happened, which is exactly the point. Now I want to know how many times did the 4 happen, right? So I'm just going to do the same thing again. I'm going to come analyze again. I'm going to classify on, same thing, just on the count. I don't actually need anything else there. And if I took the time to rename these fields, which I'm not going to do because we need to get moving along here, this is the cases where how many different sets of numbers repeated 4 times?
Yeah, 5 of them.
5 times. So across all of the possible draws, we had 5 different instances where 4 of the 742 matched.
Yeah. So to me, it kind of now seems a little bit likely that...
It's starting to smell better, right?
Yeah.
It's starting to smell better.
But this is just one simulation as well.
This is just one simulation as well. So skip ahead a few minutes if you're not interested in the use of ACL. But I'm just going to quickly say the next piece is how do I automate this? So I'm just going to come in here. I'm going to take everything from the time I delimited
So
down.
basically you're saying you don't want to have to do all that manual copy and pasting 1,000 times.
Exactly. So I'm going to save these items to a script, automate, draw analysis. So that captured straight to the script. I thought that script looked a little long. Run it here. Of course, I didn't write a proper script that turned off the safety, but now here it does that exact same thing we'd already done that we did before. All is now completely automated. So I actually wrote a good version of that. I actually wrote a proper version of that I cleaned up. So I like to keep my ACL a little bit better organized than what it does by default. So I'm going to get rid of this stuff that we just created. And in my scripts folder, I have an automation folder that called simulate draw population. Now I've done a few things here. This script down here is exactly what I just showed. This is just completely automating that manual analysis of summarizing the results on a given population of 742 draws.
Right. So it gets one population, does all the things that you just showed manually.
Correct. Now, something really neat about this is another pro tip for using ACL. Something really neat about random.org is if I change the URL a little bit, it gives me a plain output of those random number generators instead of the one that's all full of HTML in that. The purpose for that, think of this as a very simple API. The purpose of that is so that you can access it programmatically and not have to manually copy and paste like I did before.
Right. Can import the data straight from the web page.
Exactly. So what I've done, this execute command, this is the execute command in ACL. It runs a Windows script, a PowerShell script that I've created, despite the fact that I despise programming in Windows, and I'm not a programmer anyway. But enough Googling, an hour of Googling, you can figure anything out. That basically scrapes that data and creates the draw file for me. So if I run this one, that's running that script. Now it's all been completely automated. And look at, on these random numbers. This isn't set up, by the way. These are totally random numbers that are coming back. But in this particular case, we had 5s. We had 2 cases where 5 numbers, or 5
draws.
sets, 5 draws matched.
Right.
In the population of 742. That is exactly the outcome in the audit report. That literally is
It's pretty
totally
cool that
random.
it happened like that.
It's pretty funny that it happened like that. But if I go back to my folder now,
But
where my source data was.
Now you need to program it to run 1,000 times and keep
I do.
all of your outcomes.
I do, but you'll see it had created that draw population text file for me automatically. So that really is the end of step 1. Completely automate a analyzing a scenario, one scenario.
Right.
Now we want to run that scenario. A whole bunch of times. I'm not going to go deep into that. I'm happy to share this file for anybody who really cares and anybody who's not Kevin and going to make fun of my ACL scripting ability. But basically now what I've done is written a set of scripts that take what we just saw, run it 1,000 times, take those summaries for each draw and append them and compile them into one large table that will have the outcomes of 1,000 versions of this. So in this particular case, I would set my variables to 1 and 1,000, go through and run this. I'm going to save the time because I already did run this. Trust me, it works. Rather than waiting for it to populate over all of those, but it basically creates this table where it says here's each simulation. So item 1, simulation number 1, is one population of 742 draws, and how many cases there were where there were draws that there were 5 occurrences, 4 occurrences, 3 occurrences, 2 occurrences, on down the line, all compiled into a single number.
Pretty cool. So what was the max? I think I saw it there, but what was the max number of occurrences that happened on any of the scenarios?
So let's start with exactly that. So let's do a statistics on. I also captured a field that was called max recurrences, and I also captured a field called five occurrences. 5 occurrences because we'll look at 5 occurrences because that's our real world scenario we had. I'm also going to look at max occurrences though to see are there in our run of 1,000 are there ones that happen. Does it happen even more than 5 times?
Right. So 5 occurrences will tell us kind of how likely it is around 1,000 simulations for 5 occurrences to happen. Exactly.
So 5 occurrences looks like, guess what? It happens a whole bunch of times. There's actually many cases where 5 occurrences, there's many 742 draw populations where there's not just 1 or 2 duplicates of 5, like what we have. In fact, the highest there's 2 cases where there were 5 times that 5 same draws happened.
I have to admit, that's not the outcome that I expected.
It wasn't the outcome that I expected either. More interestingly, there was in fact one case where there was one population of 742 draws where one draw reoccurred 8 times.
Wouldn't it be great if you could figure out which one that was and you could just run those numbers each time and win the lottery 8 times?
Does show the potential for vulnerability. So I'm going to get things moving along. There's a whole lot more here we could analyze, but what I want to do, I have written one more script. I'm going to run it. Basically what it does is it publishes my results as the person who's capable of writing a scenario analysis. I'm going to publish my results into ACL GRC where I can share it with other individuals. So now we're in the web interface. This actually published the real results that we just got from our set of 1,000 runs, 1,000 simulations. And right away, what I can do is I love this feature. Actually, this is one of my favorite features. Is what we care about were the 5 occurrences. It will just create for me a data distribution, and when I click on that, in literally 1 second now, I can see how many This is the count from amongst the 1,000. How many times did 5 occurrences occur once? 354 out of our 1,000 simulations, there was occurrences of 5 draws matching. This is the punchline. 166 times out of 742, we would expect to see 2 different sets of 3 numbers recur 5 times.
So over 16% of the time.
Had it have been 4 or 5 cases of that instead of just 2, now we'd have a question to answer. That's much more less likely to happen. But this is pretty reasonable. 166 out of 142.
Yeah.
More interestingly, I love heat maps. And this data, with this same table data, I can create this heat map. I'm going to try and explain this in a way that makes any semblance of sense.
All right.
Across the bottom, we have that same qualifier. This is basically yes or no. Was there 2 different draws that occurred 5 times in the population? It also, then on the y-axis is what was the maximum number of occurrences.
Okay.
Does that make sense?
Yep.
So ours fell right into here. The maximum number of duplicate draws was 5, and that happened 2 times. 149. I would call that, on just a pure sliding scale, that's in the not real hot zone.
Right.
Now, of course, in most cases, that doesn't happen. It was like the very first one that we did, where you only get sets of 4. But notice, in every case, you get sets of 4.
Oh,
all 1,000 times, you get
a set of 4
draws that recur 4 times.
Interesting.
There was one outlier where not only was there one draw that occurred 8 times, there were 2 more different draws that occurred 5 times each. That would have been a smelly, if we lined up with that, that would have been a smelly scenario, right?
Basically a 1 in 1,000.
Based on this case. So there's a whole bunch of other things I wanted to show you. We've gone too long already. There's a whole bunch more you can do in really simple scenario analysis here. But it gets back to what really was the punchline. Most importantly, frankly, this whole risk analysis and scenario model, in all, I did it in an afternoon. It's really not that complicated of an exercise to do once you decide on those 3 basic, I want to be able to do this.
Right.
The outcome on the case we've already talked about. Based on our scenario modeling, we would expect what happened in the real world to happen in 166 cases out of 1,000. That's probably not, that doesn't intuitively, what it seemed like an intuitively severe risk is probably not actually a very severe risk.
Yeah, so what they brought the statistician in to help them identify whether there was an actual problem or not. Had they done some pretty basic, without using advanced statistics at all, just doing some basic scenario analysis, they would have been able to come to the same conclusion the statistician did.
That's right. And I think the more important piece is they had an event, so they were under investigation. I'm sure they wanted to use third parties anyway. But there are, I don't care what industry you're in, there are meaningful risks that you could apply this process on and do scenario analysis like this, certainly in a day or 2, let alone an afternoon, to get a real perspective on that risk, a real quantified. Out of 1,000 times we drive the business down this highway, how many times is the bridge going to collapse? Right? That's meaningful insight, and the sort of thing that if you compare it to the risk of the bridge collapsing is high, medium, or low, how much more impactful is it to say we modeled this scenario, we simulated it 1,000,000 times, we think it's 1 out of 100 times that we're going to have a problem. This is a risk we should take.
Right.
Or conversely, that might occur 16 out of 100 times. That's probably above our tolerance, and we need to think about how to control it better, buy an insurance policy, whatever we need to do.
Yeah, well, that's pretty cool. Thanks, Dan, for taking us through that today.
Sorry it was so long. That's scenario modeling in a nutshell. We'll look forward to your feedback. See you next time.
Cheers.
To not getting drunk while I explained all that.